So this particular video session, we will deal with the topic of diffraction. And this also is a continuation of YDSC. It's based on principle of interference. Let's understand diffraction. And what we have in the syllabus is basically Fraunhofer diffraction. So in that case, the wave front which is reaching a ray which is incident on a slit here. See, in this case also, what we take as a diffraction, we take a standard case of single slit. And so unlike YDSC, there are two slits here. The width of the slit is A, not the spacing. Width of the slit is A. And what is diffraction here? In case of, if we follow basically ray optics or geometric optics, it should have formed, if rays are parallel, it's coming from source at a long distance, it should have formed basically bright spot of the same size as the slit, and rest of the thing would have been should have been dark. But what we actually observe is something like this. Here also we observe a fringe pattern here of varying intensity. And light tends to reach even in those areas which are supposed to be shadow. That's a diffraction due to single slit. So let's see what diffraction and its parallel wavefront. So wavefront which is incident on the opening or single slit here is a parallel to it. So let's understand what does it mean here. So here all points, if this is a wavefront here, and all points are in the same phase. And other key difference compared to YDSC is in YDSC we take only 2-point sources. Here this is an opening here, and we take the opening size is finite. So how many points are there in the finite opening? There are infinite points. There are how many sources? There are infinite number of sources here, and we consider each as a secondary source. So here, this opening is not one source. Each one becomes a source of new light wave. And that's how do we solve. So let's say slit width is A here, and this is source of secondary wave. Let's analyze here. And from here, let's first take point O here. Just for purpose of illustration, we'll understand here because see, infinite number becomes a little difficult to comprehend. So let's say here, this entire slit opening, we divide into narrow equal width part. And if we divide how many parts, we are divided into 120 parts. So you see the reason also why 120, and all 120 equally spaced, so all have equal intensity on the screen. And let me name it. So what are this? Not S1, S2, they're S1, and other extreme is S120. Now these are the ones. So this is how we number. We can number in any manner. Now we follow. If we look at based on interference principle, do we justify that O will be central bright fringe? Yes, we can justify. See, there are how many? There are 120. If I take here 120, it means it is interference of 120 phasors, and phasor is nothing but vectors. And vector, when we take the sum, we can take the sum in any order. Result remains same. So we can always choose a the way it becomes convenient. So there are 120 sources here. How do I pair it up? I pair one extreme with the other extreme. S1 with S120, because both are symmetrical about the perpendicular bisector, hence they will have equal path length. So S1 and S2 will have constructive interference. Similarly, S2 and S19 will have constructive interference, and so on and so forth. And again, we take the sum of sum. Basically, we can easily we can arrive at this easy logical way. We can come to that conclusion that this point will be central bright fringe. All are equidistant. We can take it like this. It has constructive interference at point O. Key question comes here: how do we identify first dark fringe? And first dark fringe is important. Once you understand first dark fringe, you can identify others also. Here also, what we do here, see, let's take a point P here, and this is where you can notice, and this is how the intensity pattern is, and this is the dark fringe here. So let's take we take this point P here in such a way that path difference at P from edges of the slit is lambda. So if I take here, what is lambda means here is, if I, in this particular case, if I take path from S1 to P and path from other extreme, S120 to P, if I take the difference is lambda. We are taken path, basically this is something extreme path difference from extreme ends or from the edges of the slit. And after taking this, if the path difference is lambda from the two ends, now we divide the whole slit into two parts. Imagine we divide in two parts, lower half and upper half. So lower half have from S1 to 1 to 50 slits, S1 to 60, and other one is 60 to 120. That many sources are there. Now what we do here, and if from here to here path difference is lambda, Path difference between S1 and S20 is lambda. Path difference between S1 and S61 will be lambda by 2. S2 and 62 will be lambda by 2. As third source, and here also corresponding third source, if we keep taking pairs here, so one source here, one source here corresponding is starting from lower end. If we keep pairing, then if we take pairs like S1 and S61, and they will have path difference of lambda by 2, and hence they will cancel out each other. Like this, how many pairs? If we take 60 pair, all of them will have lambda pair path difference of lambda by 2, similar logic, and all of them will cancel out. So that's how we arrive at, thus we simplify a case of infinite number of sources. We could have done a slightly different way, but this is something perhaps it makes more intuitive sense. If I assign a number to, we make this infinite sources into some finite number of sources, though large number of sources. So in this fashion, what is the condition? What we have arrived at? Path difference from two extreme end is equal to lambda. And here path difference, if I go similar logic, if I drop a perpendicular, the way we calculated path difference in IYDSC, if this angular position is theta, this is slit is small here, this also is theta, this also is theta. Path difference is this distance, which is a sine theta. So there between this is there is slit spacing was d. Here slit opening is a, path difference becomes a sine theta. A sine theta is equal to lambda. That gives you angular position of first dark fringe plus theta, similar minus theta also. That would be angular position of first dark fringe on the lower side. Or we can say the central bright fringe will subtend an angle is equal to 2 theta. Okay, so angular position of dark fringe. In a way, this position is in a way similar to, here it is corresponding to lambda. It is similar to first bright fringe of YDSC in terms of similarity we see here. How do you find second dark fringe? This is the method we use to find first dark fringe. Second first dark fringe, again, let's take a point here. The path difference from the edges of the opening is equal to 2 lambda. The path difference is 2 lambda. And in that case, what we do, we divide conceptually, we divide the slit opening into 4 equal parts. So if total there are 120 sources, each one will have 30 sources. And again, so S1 and S31, the phase path difference will be equal to lambda by. Total is 2 lambda divided by 4 lambda by 2. And so basic path difference between extreme ends of 1/4 of the opening will be equal to lambda by 2. So if I take one source here and one source here, and likewise you keep taking pair, the path difference between such pair will be equal to lambda by 2, and all will cancel out each other. So first dark fringe, we divided the opening into 2 parts, path difference lambda. Second dark fringe, we divide the opening into 4 parts, path difference is equal to 2 lambda. Third dark fringe will correspond to 3 lambda, and conceptually we divide this opening into 6 parts, 6 equal parts. Okay, so condition for nth dark fringe, angular position of nth dark fringe will satisfy this condition. A sine theta is equal to n lambda. So we have arrived at condition for dark fringe, and bright fringe, of course, will form exactly between dark fringes. Let's try and understand what is the logic behind bright fringe. Let's move on to bright fringe here. Let's try and understand here. So before we do bright fringe, see, we have arrived at angular position, and very similar to YDSC, we can also define this position in terms of y coordinate. And if I have to find the y coordinate here, and assuming theta to be small here, see angular position, if theta is small here, what would make theta small here? Theta would be small only if a large number of fringes are forming here. Okay, if A is much larger than lambda, then only theta will be small. Theta will be small when A is much larger than lambda. And then again we take region near to the central bright fringe, then I can find the position of first dark fringe. I will substitute in place of sine theta, y by capital D. So y coordinate of first dark fringe is lambda capital D by A, very similar to YDC. Let me call this also as beta fringe. This is beta term here. We'll define what does beta mean here. So this is beta here, which is in terms of formula very similar to YDC, right? And a similar way, if I continue, this is for lambda first dark, second dark fringe, it will form at a distance 2 beta, 3 beta, because all proportional. So the y coordinate will become like this. And if this condition is satisfied, what we find? Yes. So basically, fringe width of first dark fringe will be equal to beta. Fringe width of the second dark fringe also will be equal to beta. Beta expression is very similar to fringe width what we had in case of YDSE, but this position is not similar. We'll come to this part here. Now let's look at this position of second dark fringe, and all is pretty okay. That part is the standard pattern it follows. How about central bright fringe? Width of the central bright fringe is defined from width between first dark fringe on the either side. This entire thing is central bright fringe. And from here, this side is also beta, this side is beta. So it tells you, it gives you an expression, the width of central bright fringe is equal to 2 beta, unlike twice the other fringes. So that's the one deviation and one difference we come across. The central bright fringe is twice as wide as other fringes. And the reason also, the first dark fringe is not forming at lambda by 2. First dark fringe is forming at path difference of lambda. That's the reason. So position of, now this clearly we can come across. Now to find the position of bright fringe, this point, if I take, this is lambda to lambda, let's take a point where path difference is equal to what? Path difference will be equal to 3 lambda by 2. So let's take a path difference of 3 lambda by 2. And when it's 3 lambda by 2, I divide this opening also into 3 parts. Part 1, part 2, and part 3. So if there were total, if we imagine 120 sources here, so this will be 40, and this will be 40, and this will be 40 sources, identical sources. So if path difference here is 3 lambda by 2, between two ends of 1/3 of the slit, path difference will be equal to lambda by 2. So here also what we find, if I take the lower two pairs, if I pair the first S1 with S41, if I pair S1 with S41, they will have path difference of lambda by 2. They will cancel out each other. Similarly, if I continue with all such pair S2 with S42 and so on and so forth, I find that 1/3 of these two cancel out each other, leaving aside only the third part. So these two, if we first bright fringe, this point here, first bright fringe, which is at the path difference equal to 3 lambda by 2. Conceptually, we can divide into 3 parts. Out of 3 parts here, 2 parts cancel out, and brightness is only because of the third part. That's the reason what we find here, the first bright fringe is brightness is much lower compared to central bright fringe. Because even here also, though this is a point of constructive interference, but this is constructive interference for part of the waves here, not all. So here again, quite a few of them cancel out each other. And so it will keep, brightness will keep reducing, and typically compared to central bright fringe, its brightness is about 5% or even less. So much lesser bright compared to central bright fringe, but that's the logic here. And so what we notice here, if I continue this logic here, yes, intensity of bright fringe is decreasing quite steeply, and intensity of second fringe is about 5% of central bright fringe. You don't have to memorize, but you get an idea why it is lower. Important is to understand why subsequent bright fringes intensity become lower. And the first bright fringe, 3 parts, 3 lambda by 2. Second bright fringe, it will be 5 lambda by 2. So how the bright fringes are forming? See, bright fringe and dark fringe, your expression has interchanged. Here, for the dark fringe, a sin theta is equal to n lambda, and 2n minus lambda by 2 for bright fringe. So we can again, so this is okay, very simple, we can do. So basically, there are similarity and dissimilarity. So let's, sometimes we get confused. So let's compare and contrast those two. So what are key differences and key similarities? In case of YDC, we take as 2 point sources. And in case of single slit diffraction, infinite sources. That's the reason why interference method of calculation becomes so different. There is interference of only 2 sources, and there are infinite sources. First dark position in case of YDC involves path difference of lambda by 2 from 2 sources. Here, in case of single slit, path difference is lambda from edge of the slit. So from edge of the slit, if we calculate path difference is lambda, or lambda by 2 from edge of the 2 parts. If you divide into two parts, each end of the two parts, path difference is lambda by 2. Or for slit opening, from two edges of the slit, if I calculate path difference at the point where first dark fringe is forming, path difference is lambda. So this is lambda by 2, this is lambda. Dark fringe lambda by 2, here lambda. And that's the region here. Yes, second part for small theta, assume the number of fringes are forming. And when the number of fringes are forming, so all the fringes which are within a small angular position, something like between 10 to 15 degree. If number of fringes are forming here, in case of YDC, every time bright to dark, any two consecutive dark and bright fringe we take, including central bright and first dark also, they are at the spacing of beta by 2. So alternate bright and dark at beta by 2. Here also what we notice here, only in CBP, from here, the first dark fringe is at beta. But from there onwards, this is beta. This will be equal to 3 beta by 2. So dark to bright, beta by 2 distance. From here to here, again beta by 2. From here also beta by 2. So here also, except for first bright fringe, here also fringes, dark and bright fringes are alternative forming at a distance of beta by 2, and which makes the fringe width equal to beta, which is distance between two successive bright fringe or two successive dark fringe is equal to beta also here, with only exception being the first one. The first bright fringe alone is 2 beta. Whereas in case of YDC, all are beta beta in the central region. So here, which makes it central bright fringe is twice as wide compared to other fringes. In case of YDC, all are the same way. And another difference what you notice in case of YDC, all bright fringes have same intensity. If two sources are identical, two slits are identical. In case of single slit, intensity is rapidly decreasing. So suppose we had a YDC, this is a single slit. And single slit, you have a pattern, single slit, you get single slit diffraction pattern, something like this, how this brightness will vary. And even this single slit also setup can be converted into YDC. Suppose what we do, we cover the spacing here, there's opening here, we put a plate here so that only small gap is left at the top and bottom symmetrically. So we cover part of the spacing. So in that case, what will happen, if I cover it like this, earlier what was single slit size of opening, that becomes the spacing between YDC. A becomes equal to D if we cover the major part of the slit, leaving very small parts here. In that case, what will happen? Yes, this is something. So if the reason I have done, if A and D are same, if we superimpose fringe pattern, that's what it would look like. So this is something here, but this one would have formed at beta by 2. Okay, and you notice here, see this something. So first this bright fringe is coinciding with dark here, then dark is coinciding with bright, and then again bright and dark. So here all except for first part here, dark and bright fringe will coincide with each other. Dark fringe of single slit diffraction we coincide with bright of YDSC if same setup is converted into YDSC. Only thing, this part, central part will be different. It will be twice as wide. Okay. So single slit opening can be converted into YDSC. A will become D and the fringe width will remain, hence the fringe width will remain the same. The value of beta will not change. Though it may signify different thing, pattern may change, but beta value will not change if I convert something like this. Okay. So, let's continue further with the same thought. Suppose we give a previous thing we are talking about how we can convert a single slit diffraction into YDSC setup by covering up the opening. Let's consider in terms of more number. Let's try and understand what kind of variations we can have. If we consider slit width of YDSC to be finite. Okay, so let's look at this case. In this case, what you're looking at, each slit will have its own single slit diffraction. See, in case of YDC also, the slit also will have certain width. It cannot be zero. It cannot be taken as just a single point here. And whatever width it has, corresponding to that, it will have diffraction pattern. And because of presence of two slit, it also have YDSC pattern. So in case of YDC also, it should have both the things here. For example, let's take example. Let's try to understand in terms of number. So in terms of here, the slit spacing is D, and let's say the slit width is one tenth of the slit spacing. So like YDC, we call slit spacing is D, but each slit also has certain width. What is slit width have is D by 10 of the spacing. So what will happen, even suppose we keep this slit closed here. If we keep this slit closed here, one, what we typically used to call in case of YDC S1, the slit one, which will have opening of size D by 10. Hence, it will form diffraction pattern on the screen, which will have fringe width, if assuming for in the small angular place, and it will have fringe width equal to beta, given by standard formula, except for center bright fringe will be 2 beta. So if both the slits are open, this will form its own single slit diffraction. This also will form its own single slit diffraction, and both put together will form YDSC. Let's try and understand, make some sense out of it. So what is the size of opening I assume? I assume the size of opening to be 1/10 of the slit separation. In that case, if I take beta, if we take these sources S1 and S2, beta is equal to lambda d by small t. That's the fringe width. So here it will form fringes, YDSC, it will form fringe pattern of a uniform spacing of this beta here. But these two openings separately, here A value is, if I take each slit as single slit, A is equal to D by 10. Size of the opening, single slit is equal to D by 10. So it will form a single slit diffraction pattern, and width of the single, what will be the width of central bright fringe due to this? Central bright fringe due to single opening. Central bright fringe creates an fringe width of twice beta. Beta is equal to lambda d by A. A is the size of opening, but A itself is D by 10. So if I put D by 10 and 2 because of central bright fringe, the central bright fringe will be 20 times as wide as the fringe width due to YDSC pattern. So we'll have YDSC. So basically I can ask the question, within central bright fringe of each opening, how many YDSC fringes will form? 20 fringes of YDSC pattern will form within central bright fringe of each opening S1 and S2. The central bright fringe or single slit diffraction will contain 20 YDSC fringes, and that number depends on this ratio. All the cases we are still making assumption all those fringes are within the small theta value, or we can have some other calculation based on this. Right, now we come to one more small subtopic called resolving power, and this is a pretty small and interesting topic. So basically, whenever we view any object either through eye or any other optical instrument is could be microscope or can be telescope. Okay, so all cases images are getting formed through optical instrument. And what we understand from diffraction, image of a far point. In case of diffraction, see, we see an object like pixel idea. Now we are familiar with the pixel idea. We see object as several point objects, and each point has a different color and shape, and that collection spacing creates such shape here. So image of a far point through a slit. So any opening, if we look at image of far point, it means whether those rays will be parallel, incident rays will be parallel to the slit opening, and opening could be a retina of the eye, or it could be lens of the microscope or a telescope. A point object or point source create a circular disc kind of image. We are talking only the central bright fringe, because central bright fringe, in case of diffraction, central bright fringe alone contains the major part of energy. So this is something, if I have 2 point sources kept at a large distance, and those 2 point sources are bright and background is dark, how the images will get formed on the screen, this is how the images will get formed on the screen. You see the center, this is basically twice beta, the diameter is equal to twice beta, and then we see faint outlines also, which will be the second bright and third bright fringe. But basically this itself will carry the most of the energy. So this is the 2 points have created image like 2 discs. This is something when what happens if the points are brought nearer, if angle between points are reduced, what will happen, even the images also become closer. So this is now I can clearly see these are because of 2, and this is something you can see this how the intensities of those 2 are. As the spacing reduces here, this is how images will look like, and in terms of intensity also we can show like this. And if they become very close, it will start appearing like if the 2 point sources are at a small angular separation. So let me what I mean by angular separation. If this is lens here and this is axis here, there's this one point here and this another point here. And if their distance, there's a distance x and this distance is L. See, they are making an angle x by L on the lens, and that based on the same angle is there between the images also. Okay, so they say this is angular separation of 2 point sources forming image through a lens. It is lateral distance between the two and distance of the object from the lens. Thus, angular separation, if that reduces, here it is clear. Here still somehow we can resolve that there are 2 points. Here we cannot. So that's the reason why point doesn't remain like point. It becomes like a disk. And moment they start overlapping, we are not able to differentiate whether it is created by 1 point source, there are 1 point here or 2 points here. And same thing goes with the line also. We'll see some example for that also. So like a circular disk, so what we notice is the Rayleigh has laid down a criteria. What should be the minimum separation which we can distinctly notice? Yes, there are two kind of things. You know, we don't have a doubt whether there are 2 points or 1 point. One central maxima of diffraction. So this is central maxima of diffraction of 1. If if it coincides with the minima of the next point, if the central maxima coincides with the minima of the diffraction pattern due to second point source, then these 2 points we are just able to resolve. If it is any closer than that, then we are not able to resolve. So that becomes the minimum criteria. So if I call each point has fringe width of beta, and so fringe width is beta means from central maxima to its minima, the distance is beta. It means the distance between two maxima has to be greater than beta. Then only you can resolve the points. This is something, and this formula what we arrived at for diffraction, that was for a slit kind of source. Point source, we have to make a small correction. That's why we come to, so what is the least angle which we can resolve? We will not go to derivation. Actually, it's not so difficult to come at. Least angle which can be resolved. Least angle is something like x by L. So least angle, will again look at some example, is equal to 1.22 lambda by t in radian. Since it is in radian, of course, in terms of dimension, numerator also length dimension, denominator also length dimension. What is lambda here? Which wavelength is being used for the object? So different wavelengths have different fringe width. That's why limit of resolution depends on wavelength also. For eye, we take most prominent wavelength or wavelength to which eye is most sensitive, which is around 550 nanometer. And what is D here? D is the diameter of the aperture of the lens. And this is the least angle which can resolve. And in case of eye, even eye also, we can see, we'll just see one example also. What is resolving power of the eye? If I have to calculate theoretically, what is the resolving power of the eye? How do I define resolving power? Resolving power in terms of theta is the minimum angular separation between two objects which can be distinguished. And you notice if I mark these 2 points here, if we are sitting close to the screen, you will have certain angle. If I mark these 2 points, this one, let maybe this is equal to 3 mm. If 3 mm, if we are looking from a distance of 1 meter, this angle will be equal to 3 into 10 to the power minus 3 by 1 meter. But if you look from 3 meter, angle becomes 1/3. So as we keep going farther and farther, angles subtended by the 2 points keep getting reduced. And moment this angle reaches this angle here, we'll not able to distinguish these 2 points as two separate points. It will look blurred. It will look like one. So what is the least angle I can resolve? It is 1 by 60 degree. In terms of degree, we can also convert it radian. This is from the radian, then convert to degree, but this is convenient to understand and remember. And this is based on practical application people have found, and which is 1/3 of theoretical value what we can calculate. So there is some reason also, just eye sensitivity and how does eye function. So this we don't have to remember, but just get an idea what it is. And let's understand, if we talk about resolving power of something like telescope, let's suppose that two different stars or different colors, and two stars are close to each other. And when they are not too close, the stars will have particular separation. There will be certain distance between the star X, two stars in the space, they are at a distance X. And we are looking at from Earth, and let's say the distance from Earth is equal to R. Then angle they are subtending on the observer on Earth is equal to X by R. So if they are appearing like this, they are fairly well resolved. Here I see this angle between them, angle separation become resolved, just resolved. And if the angle is too small, we will not even differentiate, it will appear like this. This is something not resolved. Okay. And this angle is just equal to delta theta angle. And this angle is greater than delta theta, minimum angle for resolution. And we can change either this theta can increase either by increasing the spacing. So if you have two lines, you want to see the two lines clearly, move them apart, or you move closer to the object. You move closer, angle becomes larger and you're able to view. If it is more than 160 degrees, less we can do that. And very good experiment is something like this. You notice here, if you are sitting close to the screen, if your monitor has fairly decent resolution, you can see several lines here, and we can spot those line patterns. Whereas you see on the right hand side, at first instance, you will think that this is something, entire thing is painted gray uniformly. But if you go close and observe, actually this also made of lines. But here spacing between line is smaller. So if whatever spacing it has, divide by the distance from which you are looking at. That's the angular separation between two lines. Here space angular separation becomes smaller. This angular separation definitely is less than 1 by 60. We are not able to differentiate between the lines. Here we are able to differentiate if this angle is greater than 1 by 60 degree. What happens, suppose you can try this experiment also. This is the resolving power and I. Just try keep this monitor on and move to a far point in the room. If you move at the far point, you notice these two will look identical. Though they look so distinct here from short distance, your eye is able to resolve dark lights and in between light bright part. Whereas we are not able to. But if you look at why you are not, when you look go at a larger distance, why these two look almost identical? Because of diffraction pattern. Basically, what will happen? Something similar here. This angle becomes smaller, and angle will become smaller than minimum angle I can resolve between two lines, and entire thing will start looking gray. That's the concept behind resolving power. Key point in resolving power is understanding this formula here. This one formula, but just knowing the formula is not enough. How do we arrive and what does it mean? And quite a few questions have come on this small topic of resolving power. And it may also come in combination with um, telescope, microscope, or even YDC and diffraction. So after this, I will take up some numericals which are based on the concept of diffraction as well as resolving power. Those two things we'll discuss after.